Good day to all. My name is Oleg Tashkevich. I am a PhD student at the University of Haifa in Israel. Today I want to present my new article to find out, does city smartness reduce income inequality and bring environmental benefits? So let's begin. Few people know that the smart city movement, such popular today, emerged in the early 1970s. And the reason for this was the dissatisfaction of the residents with the traditional models of urban planning, since the cities were planned as high-density buildings and not as places serving the needs of residents. The smart city movement aimed to change this paradigm by integrating ICTs into the city management as means of improving urban services and quality of life of urban residents in general. As cities become smarter, they are expected to offer better solutions to various modern urban problems, such as uneven access to services, income inequality, and environmental degradation. Modern examples of smart cities are London, Singapore, Tel Aviv, Barcelona, Dubai, etc. These cities are already using a wide range of high-tech solutions that offer personalized information and services to their residents, help to improve the efficiency of resource use, monitor air pollution, and of course optimize road traffic. Today, cities can apply different strategies for advancing urban smartness. For instance, cities can deploy diverse ICTs solutions that collect digital data from various sensors and monitor ongoing changes in the urban environment. The most prominent examples of such smart ICTs systems include the 5G ecosystem in Espoo that provides ultra-fast internet connectivity and the sensor web bike system that helps to assemble air quality information in circles. The creation of higher education institutes and the encouragement of innovation are two other popular strategies for advancing urban smartness. Today, cities that aspire to rank high on the urban smartness scale tend to host numerous universities and colleges and provide tens of thousands of well-paid high-tech jobs. It should also be said that the smart city concept has already generated considerable interest. Thus, according to Google Scholar, more than 1.7 million articles and scientific reports have been published on the smart city topic today. Previous studies demonstrate that smart cities lead to a cross-border increase in population welfare, improve environmental conditions in cities, reduce resource consumption, and thus help to prevent environmental degradation. Yet other studies point out in the opposite direction, showing that smart cities aggravate income inequality and lead to the deterioration of the environment. What conclusion is more correct is ultimately unclear. Thus, the main objective of the study is to investigate the relationship between the level of city smartness on the one hand and intra-urban income inequality and environmental conditions in cities on the other. In the present study, we aim to answer this research question using the most recent data available for year 2020 from different databases maintained by the World Bank, OECD, the World Meteorological Organization, and others. The analyzed cities are located on 6 continents, which represent the main regions of the world. The analysis of previous studies of the smart city categorization criteria helped us to identify 48 metrics commonly used by empirical studies for estimating the level of city smartness. Then we selected out of this number 9 most frequently used metrics. The selected metrics evenly represent the 3 main dimensions of sustainability: economy in technology, society and environment, by including 3 metrics into each group. As you can see, 2 indicators, overall air quality index and Gini, are used in the analysis as dependent variables. Air quality index is an important measure of environmental performance due to its ability to estimate overall air quality in cities. The main advantage of this index is that it converts concentrations of different air pollutants into a single. Gini is one of the multiple measures of intra-urban income inequality. In this study, we used the Gini index due to its ease of interpretation and the availability of index calculates for different geographic units, including major cities. As for control variables, we included population size and GDP per capita as potential predictors of air quality index and Gini in cities. Population size is one of the most important indicators of urban development because populous cities are often most productive due to intense competition and knowledge spillover, but often lack in environmental performance due to high traffic volumes and concentration of production facilities. GDP per capita is another important measure of urban development since higher incomes are associated with quality of life as well as with better environment performance. Additional variables used in the analysis as controls were capital status and latitude. As previous studies show, these variables, alone or in combination, help to explain urban performance, which justify their inclusion into the list of predictors in this study. According to our initial hypothesis, city smartness is significantly associated with less income inequality and better environmental conditions in urban areas. The general equation for our regression analysis is shown on the current slide. Here we can identify 3 vectors: vector of city performance measures, vector of smart city attributes, and vector of control variables mentioned earlier. Pearson correlation coefficients between individual smart city metrics are reported in the current table. As evidenced by this table, several metrics emerge as strongly collinear. These pairs of metrics are innovation index and happiness index, number of wireless access points, and number of universities. Similar results for the second part, innovation index and government development index, etc. As the use of collinear metrics in a multiple regression analysis might bias regression estimates, we extracted uncorrelated components, in other words, factors. As evidenced by the table, 3 separate factors are extracted as underlying dimensions of the 9 original smart city metrics. The first one is strongly and positively correlated with the innovation index, happiness index, government development index, and environmental health and ecosystem vitality. Those factors can be termed innovativeness, smart government, and ecosystem vitality. The second factor correlates strongly with the number of startups and the number of air quality monitoring stations and can be thus termed as startups and air quality monitoring. The third factor has strong positive correlation with the number of wireless access points and the number of universities and can be termed higher education and internet access. These 3 factors jointly explain over 74% of the original variable's variation. Based on the results of stepwise regression, factor 1 emerges as statistically significant predictor of both income inequality and air quality in the cities under analysis. In the models estimated for both Gini and AQI, the factor has highly significant negative associations with the dependent variables under analysis. It's model 1A, and the following model also approved this result, model 2A. This indicates that as the values of the factor increase, income inequality and air pollution in the study cities tend to decrease. Notably, neither factor 2 nor factor 3 emerge as statistically significant predictors of either Gini or AQI. In addition, only one control variable, population size, emerged in a model 1A as statistically significant for Gini. The results of our study demonstrate that a reduction in income inequality and air pollution in cities are both associated with several performance metrics linked to innovativeness, smart government, and ecosystem vitality. The study also reveals the absence of significant links between intra-urban income inequality and environmental performance of cities on the one hand, and the scope of technology proliferation and air pollution monitoring on the other is a rather unexpected outcome. As we explained this result, the availability of technology does not necessarily lead to its adoption, and the pace of ICTS adoption by different population groups is not always fair. Somewhat surprisingly, we find no evidence that the proliferation of internet technologies and the number of universities the city hosts are related to either intra-urban income inequality or environmental performance of cities per se. We attribute this result to the fact that internet proliferation and more places of higher learning might create opportunities for better in cities, but do not guarantee that these opportunities are realized. We thus recommend that transition of cities towards greater smartness should be focused on people's needs and skills of using ICTS, not on ICTS per se. The smart city transition process include facilitating ICTS access to all, including the elderly, lower income population strata, and people with disabilities. Additional measures might include providing a 24/7 technical support, enabling citizens to report urban problems in real time, and encouraging grassroots level citizens initiatives in environmental monitoring by making such reporting options more accessible and affordable to all. As the present study reveals, a popular belief that simple packing cities with ICTS tools can help generate positive environmental externalities and reduce intra-urban income inequality is apparently wrong. Therefore, to achieve a real improvement in environmental performance and to reduce urban inequality in cities, ICTS tools which cities employ need to offer effective solutions to specific urban issues that particular cities face, and to increase the efficiency of specific urban services. I will end on this. Thanks